है? क्या कह रहे हो?
Hello everyone, am I audible? Hello, मेरी आवाज आ रही है?
Yes, sir.
ओके, और स्क्रीन शो हो रही है मेरी? स्क्रीन शो हो रही है?
Yes, sir.
Okay, let's begin. So last time we proved Riesz representation theorem. Okay, so let us recall what Riesz representation theorem was. So Riesz representation theorem says that we have a Hilbert space. H is a Hilbert space. Okay, and say we have a linear function, bounded linear functional f. So on H dash means H dash is the space of all bounded linear operators. So functionals. So f is a bounded linear functional on H. Then there exists a point, a vector z in H, such that f of x is given by this inner product. Okay, and furthermore, norm of f is same as norm of z. Okay, so now let us ask one question. Ask one question that so now we ask, suppose we have f in dual space, that is the
सर आपकी
bounded.
वॉइस ब्रेक हो रही है.
क्या सबके साथ ऐसा है? हेलो, क्या सभी के साथ ऐसा है? मेरी वॉइस हेलो
सर क्लियर है.
क्लियर है ना? तो जिनका वॉइस ब्रेक हो रही है तो उनका नेटवर्क ठीक नहीं होगा, तो उसमें मैं तो कैसे हेल्प करूंगा बताइए आप.
सर आवाज नहीं सही आ रही है आपकी.
इसका कारण आपका नेटवर्क खराब है, ठीक है, इसमें मैं कुछ नहीं कर पाऊंगा. तो आप ठीक नेटवर्क में आइए, बाकी लोगों को सुनाई दे रहा है. Okay, so we have a bounded linear functional. Now we ask, so just by using this representation, can we find this z? So see, in this representation theorem, we have only the existence of z. We cannot find z. Okay, we cannot determine using all from Riesz representation theorem. Riesz representation theorem says that there exists a vector such that this any bounded linear functional can be given by an inner product. This much Riesz representation theorem says. Now we want that particular z. Okay, so we take a bounded linear functional, and now we want z. What is this z? So for we can determine this if we are in some good situation, like suppose we are given an orthonormal basis. Okay, so ei to say okay, so suppose we know an orthonormal basis of H is an orthonormal basis, then do you know how? So any vector x can be written as a linear combination of these ei. And can anyone recall what was that linear combination when ei's are orthonormal? We have a special form for this. Can anyone recall?
The inner product xei or ei?
Inner product x ei. This was the linear combination. Okay, so we want z. So z will be in this form. Z will be z ei. Correct. And from here, from Riesz representation theorem, you know if f is in h dash, then fx is nothing but x z for all x in h. Correct. This is by Riesz representation theorem. Okay. So in particular, put x equal to ei. You get fx equal to ei comma z, this inner product. Okay. Sorry, I should write here ei, since I am putting x equal to ei, write ei. Any problem? And this is true for all I, 1, 2, and so on. Okay. So if you see the relation, so what was z? Z was e z ei, and you know this z ei is same as ei z bar ei, correct? But ei z is f of ei, so this is f ei f ei bar. So what do you get? So you get if E1, E2, En is an orthonormal basis, then for any f in h dash, okay, then for any h in f dash, we have z equal to summation f ei bar ei, so that fx equal to xz for all x in H. So you determine Z for this F. Okay. Any doubt?
No, sir.
Okay. So now I'll give you another something called weighted inner product. This is simple exercise for you. So let's see what it is. So suppose we are in L2, okay, and mu I be a bounded sequence. This is a bounded sequence of positive numbers, positive real numbers, okay, and say x and y, and say x and z, these are in L2. You all know what L2 is, okay. We now define an inner product which is called weighted inner product. So we are using this weight mu, x mu z. So if you remember what is inner product in L2, what is the uh, inner product in L2, you know. So in L2 this is nothing but xi zi bar. This you have already seen, inner product in L2. Now we define x z mu. This is called weighted inner product, and we define it like this: mu I, alpha I, beta I bar. Okay. Where this mu I means mu is mu1, mu2, and so on. This is a bounded sequence of positive numbers. So you have to prove that x, z, mu, or rather inner product. So this is an inner product. So for this, what you have to do, you have to satisfy all the properties, all the axioms of inner product. It's easy. So this part is easy, you can do it your own, and this is called, this inner product is called weighted inner product. Okay. So in this lecture we will not see any application of this, but it is very much applicable. Okay. Then next question is, if this is an inner product, so question arises whether L2 with this norm is L2 with this norm Hilbert space. So for this, what you do, you have to check whether L2 with this norm, with this inner product is complete. So this completeness, this concept is based on metric space theory, metric space structure. But you know, every inner product gives a norm, and norm gives a metric. So we can talk about completeness. Okay. So it is very easy to see because we have already seen L2 a complete space in when we were discussing norm. So the same process is same, but here is one catch. So since we have these mu i's and these are bounded positive numbers, so what happen if, so what is the condition on mu so that it form this L2 with this inner product is complete. So there is when you, so it is an exercise for you. Find the condition on mu so that L2 mu is complete. Okay, so mu has this property, mu is bounded sequence of positive number. So what is extra condition that mu should satisfy? What would be the extra condition that mu satisfy so that L2 with this inner product is complete? So this is an exercise.
सर रिजल्ट पुरानी कुछ रिजल्ट्स यूज होंगे इसमें?
हाँ, मीन्स आपको देखना है L2 कंप्लीट आपने देखा हुआ है L2 कैसे कंप्लीट हम प्रूव करते थे, ठीक है? आपको क्या देना है, आपको दिखाना है कि हर कॉशी सीक्वेंस कन्वर्ज करती है, ठीक है? तो आप L2 में कोई कॉशी सीक्वेंस लेते हो, उसकी मदद से आपको याद है कि हम कहीं भी L2 जहां पर भी हम L2 ले रहे हैं जिस फील्ड में, हम फील्ड में कॉशी सीक्वेंस दिखाते हैं, क्योंकि फील्ड में कॉशी सीक्वेंस कन्वर्ज करती है तो हमें लिमिट मिलता है हर एक मीन्स आपको इस। सो आप क्या करते हैं, से एक्स अल्फा कॉशी सीक्वेंस लेते हैं, एक्स अल्फा क्योंकि एक खुद एक सीक्वेंस है, तो ये आएगा कुछ x1 अल्फा like this, x11 x1, so this is say x1 this, so something like this. Then x2 will be x21 x22 and so on, then x3 x31 x32 and so on. You did like this. So we are taking this sequence, this is Cauchy sequence in L2. So using Cauchy, so using Cauchy sequence in L2, you get these are sequences in R or C wherever you are. So these are Cauchy sequences. So they will converge to somewhere. Say this is converged to say x1, this is converged to x2, and so on. So finally you get something like this, x1, x2. So after getting this, what you have to prove that this belongs to L2 and prove this converges to this vector. This is what you did in Banach space theory. Okay, करेक्ट? अगर याद आ रहा हो तो हम ऐसे ही कुछ कर, सब में लगभग ऑलमोस्ट यही तरीका था। हम कॉची सीक्वेंस ले रहे थे, कॉची सीक्वेंस की मदद से हमको सीक्वेंसेज मिल रही थी कहाँ पर, फील्ड में, क्योंकि फील्ड कंप्लीट ले रहे हैं हम, जो भी काम कर रहे हैं वो कंप्लीट फील्ड में है, आर और सी दोनों कंप्लीट होते हैं, और उसकी मदद से आपको दिखाना था कि L2 कंप्लीट था। तो वही जब आप ये करेंगे तो आपको म्यू, क्योंकि हमारे इनर प्रोडक्ट के पास म्यू है, ठीक है, जो भी नॉर्म यहाँ से आपको मिलेगा वो म्यू पर डिपेंड करेगा। ओके, जो भी नॉर्म है वो म्यू पर डिपेंड करेगा, तो आपको कुछ कंडीशंस मिलेंगी म्यू पर, तो वो कौन सी कंडीशन है जिससे कि ये कंप्लीट होगा, या आपको फाइंड करना है। Okay. Clear? So, so you with those conditions, whatever you satisfy, and such that L2 is complete with respect to this norm, then since L2 is complete with this norm, this means is a Hilbert space. Is a Hilbert space, and let me write what that condition is. So you will find here, and I'm telling you what that condition will be. So the Hilbert space if infimum of mu I, this is positive. Okay, so this means mu I cannot be like this 1, 1 by 2, 1 by 3, and so on. This cannot be a mu. This will not give you the complete L. This will not make L2 complete. Okay. So because its infimum is 0, so it is not of this form. Okay. L2 is Hilbert space. Therefore, any functional bounded linear functional f for any bounded linear functional f in L2, we have a vector z in L2. Okay, for f in L2 dash, for f in L2 dash, there exists z in L2. Okay, say z equal to beta I. So z is a sequence in L2. Okay, such that f of x equal to x z mu. And you know x is a sequence, in fact, since x belongs to L2, it is a sequence. So this is, say, x is alpha 1, alpha 2, and so on. So from here, what you get, summation mu I, alpha I, beta I bar. Okay. So, and what is norm of f? Norm of f is norm of z. This is by representation theorem. And what is norm z? Norm z is z z mu half. Okay. So what it is? Okay. So this is summation mu I, beta I bar. But beta I bar is mod of beta I square. Okay. This is how you will get norm of f. So so this was some examples where we use Riesz representation theorem. Now, if you remember when we were in Banach space setting, so we were always interested in, if we have a Banach space, then we ask what is its dual space. In fact, when you computed such things, say what is the dual space of LP. Okay, can anyone tell me what was the dual space of LP? So you know LP for 1 less than P less than equal to this, LP was Banach space, but it's not a Hilbert space except for P equal to 2. Okay, for p equal to 2, LP is a Hilbert space, otherwise it is not. So this is a Banach space. What is its Banach space? What is LP dash? Do anyone remember this? किसी को याद है? आपके पास एक हिंट देता हूँ, 1 by p plus 1 by q equal to 1. अभी किसी को याद है? Hello? And what was L1 dash?
डैश तो सर एल इन्फिनिटी होगा डुअल
L infinity था. What was LP dash?
इसका चाहिए
LQ था, where Q satisfies this thing. They are conjugate. P and Q were conjugate. था ऐसा? अगर आप भूल गए तो फिर से उसको देखिए. ठीक है? कोई दिक्कत इसमें?
नो सर
Okay. So since we were talking about dual space or Banach spaces, we talk about dual space of Hilbert space as well. Okay, so what we find, the dual space of Hilbert space, they are isometrically isomorphic to Hilbert space itself. Okay, यहाँ पर ऐसा नहीं था. Banach स्पेस में था कि L1 का डुअल क्या मिल रहा है आपको, L infinity मिल रहा है, LP डैश का डुअल आपको LQ मिल रहा है, where there is a nice relation between P and Q. Okay, so let's find what is the dual of L2. Okay, the dual of L2. You can easily guess it from this relation. You can easily guess, but this will give you a nice observation for general Hilbert spaces. Okay, so what would be dual space of L2? So here dual means space of all bounded linear functional. Okay, so L2 का dual आपको क्या लगता है, क्या होना चाहिए?
L2 ही
L2 होना चाहिए. ऐसा क्यों लगता है?
सर 1/2 + 1/2 = 1 होगा.
ओके, ये तो आपने गैस किया वहां से, ठीक है, लेकिन अब ऐसा है तो आपको प्रूव करना पड़ेगा. So for this what you do, you define a map T from L2 dash to L2. Okay, which is linear, which is 1 1 on 2 and norm preserving. Okay, so what you do, take any f in L2 dash. आपने कोई भी एक L2 dash लिया, सॉरी एक बाउंडेड लीनियर फंक्शनल लिया L2 का, करेक्ट.
यस सर
नाउ you want to define T so that T of f would be a vector, a unique vector in L2. Okay, some vector here in L2, but how would you choose that vector? So for this you have a Riesz representation theorem क्या कहता है रिप्रेजेंटेशन थ्योरम? किसी भी बाउंडेड लीनियर फंक्शनल के लिए फॉर ईच एफ इन L2 dash there exists a z which depends only on f. ओके, अब मैं उसको वहां z लिखा था क्योंकि यहाँ पर मुझे फंक्शन दिखाना है, तो मैं सॉरी एक t डिफाइन करना है, और जो भी चीज मैं इधर लिखने वाला हूँ वो डिपेंड करेगा f में, तो इसलिए मैं उसे zf लिख रहा हूँ. देयर एग्जिस्ट zf in L2 such that f of x equal to x zf for all x in L2. So this zf is unique vector corresponding to f. We have zf. Okay, so just define t of f as zf, where zf is this vector which comes from Riesz representation theorem. Okay, define this. So prove that t is linear, and it's easy to see tf plus z equal to say zf plus z. Okay, आपको प्रूव करना है कि zf plus z जो है वो ये लीनियर है, आपको ये प्रूव करना है, और ये प्रूव करना इजी पड़ेगा आपको. कैसे? ओके, तो यहाँ पर ये क्या काम करता है? ये काम करता है f plus z of x equal to x comma z. हाँ, ओके. Okay, so we have this thing. T f plus g. एक मिनट थोड़ा सा वेट करिए. इधर से मुझे जाना है कहाँ? एक्स जेड है प्लस जेड जी आना चाहिए. T f plus g would be some z of f plus g. T f plus g is in L2. Okay, so this is of this form. एंड ये वाला जो पार्ट है ये क्या होगा आपके पास? दिस इज एफ एक्स प्लस जी एक्स, एंड यू नो फॉर एफ एक्स यू हैव
x
एफ एक्स इज नथिंग एक्स जेड एफ, और जी एक्स इज नथिंग
x
एक्स जेड जी. ओके, so this as whole, this is x comma zf plus zg. Okay, so using this, what you get, this zf plus zg, sorry, this is nothing but zf plus zg. ओके, और जो ये था tf, दूसरा था tg. ओके, so this you will find from this relation. Correct? So in this way you नहीं, एक और चीज आपको प्रूव करनी पड़ेगी. t अल्फा f, यहाँ पर क्या ये कंजुगेट लीनियर तो नहीं होता? देखते हैं, शायद ये कंजुगेट लीनियर हो सकता हो. एक मिनट चेक करते हैं. सो दिस इज z ऑफ अल्फा f, बट ये होना चाहिए अल्फा एफ एक्स इक्वल टू एक्स कॉमा जेड अल्फा एफ, और ये क्या चीज है? ये अल्फा ऑफ एक्स जेड. सो ओके, यहां से ये आया क्या, अल्फा जेड एफ, which is so using this relation, this t of alpha f will be alpha of zf. Okay, so this is linear, ये प्रूव करना इजी होगा. And this is 1 1 comes from Riesz representation theorem. And why it preserves norm? Because from Riesz representation theorem you have norm f is norm zf, and this is more this. Okay, so this implies dual of L2 is L2. The dual of L2 is L2. Okay, इसको आप और जनरलाइज कर सकते हैं. So what is theorem? Theorem says, suppose we have a Hilbert space, let H be a Hilbert space then the mapping T from H to H dash. Okay, यहाँ ऊपर हमने H dash से H में डिफाइन किया था, याद करो, ये L2 dash से L2 में था. अभी हम H to H dash चल रहे हैं दूसरे डायरेक्शन में. is bijective, defined by, so how did we define this, how do we define this? This is TH is given by T of Z equal to FZ. Okay, what is FZ? ये हमने पहले दिन किया था जब रिप्रेजेंटेशन थ्योरम कर रहे थे, याद करो. दिस ZF is XZ. ओके, आपको याद है ये हमने किया था. अगर मैंने लिखा होगा तो वो मैं दिखाता हूँ आपको. Here, so we define this. See, for any fixed z in an inner product space, we defined fz as this inner product. Okay, so zx equal to this inner product ओके. वो पेज में थोड़ा दिक्कत है, मैं दोबारा इसको लिख रहा हूँ थ्योरम को. तो थ्योरम says we have H, a Hilbert space, and we have a map T from H to H dash given by T of Z equal to Fz. Okay, this function is bijective, T is bijective, then T is bijective and conjugate linear. It's not linear but conjugate linear. What is conjugate linear? Conjugate linear means T lambda Z equal to lambda bar Tz. This is conjugate linear. So how do you do this? So what is T lambda Z? T lambda Z will be F lambda Z. Okay. But this T lambda Z is a functional. Okay, this is a functional. So this means this is an element in H dash. So from there, what you do, you apply this T lambda Z to some vector x of H. So this is nothing but F lambda Z of x. This is nothing but x lambda z. Now use प्रॉपर्टीज ऑफ इनर प्रोडक्ट. ये सेकंड कोऑर्डिनेट में है. लैम्डा जब बाहर निकलेगा तो लैम्डा बाहर हो जाता है, आपको मालूम है ये. z. So this xz is nothing but f lambda, sorry, fzx. This is fzx lambda bar, and this fzx is t of f of x. So from here what you get, t lambda z equal to lambda bar tz. Okay, other things are easy to see. It is 1 on to everything is easy, and second part, say tz plus wx. So proving this is also easy. What you do, you apply tzw to a vector x, so it will get, so from here you will get this is fzw to x, so it will be xz plus w. Now use properties of inner product. This is xz plus xw. Xz is, this is fz, this is fw. Okay. So okay, so let us observe few more things. Okay, so we define h dash as bounded linear functionals. Okay, so this K is complete. K always complete. If H is the inner product space, if H is IPS, inner product space, we are not saying it is a Hilbert space, just an inner product space. Then you know, you have already seen this in Banach space theory. So since H is inner product space, it is a normed space. Okay, and K is a Banach space, is complete normed space. Complete normed space. So H dash is always a Banach space. H dash is always a Banach space. Whether H is Banach or not, it does not depend on H. As soon as H is a normed space, H dash is Banach space. And what was the norm there? So norm is supremum over mod of fzx, where x here and norm x equal to 1. Oh, so this is h, not h. Okay. But how did we define fzx? This is inner product. Okay. So when H is an inner product space, we have norm of F that is this thing. Okay. But we can say more if H is a Hilbert space. So if H is a Hilbert space, so we have this theorem. Let H be a Hilbert space. Then H dash is also a Hilbert space. With respect to an inner product space. Sorry, what I am saying. HB, let H be a Hilbert space. Then what I am saying is H dash is also a Hilbert space. But when I say Hilbert space, it means there is an inner product in H dash. Okay, it is already complete. H dash is already complete normed space. But for saying it a Hilbert space, we have to show that there exists an inner product. So H dash is also a Hilbert space with the inner product defined by. So take two bounded linear functional and define this. So see, for f by Riesz representation theorem, you have ZF. And similarly for G, you get ZG. Correct? So you define this inner product H as this. F comma G in H dash. Where F comma ZG both belongs to H and they are unique element corresponding to F and G, okay, as where these are unique vectors in H corresponding to F and G respectively as the Riesz representation theorem. So you have just proved that. So this is an exercise for you. Prove that Fg is an inner product. So this means those four properties you have to satisfy, and everything else this is done earlier because we have already seen that S dash is a Banach space. So since we have already seen that S dash is Banach, so it means it is complete, and a complete inner product space is Hilbert space. Okay. Any doubt?
प्रोडक्ट दिखाने के लिए हमें तो सिंपल इनर प्रोडक्ट दिखाते वैसा ही दिखाना है ना।
हाँ, जैसे आप सिंपली इनर प्रोडक्ट दिखाने के लिए करते ना, वो तीन चार प्रॉपर्टीज जो भी थी वो आपको सेटिस्फाई करवानी पड़ेगी। अब हमने यहाँ पर बात करी और अगर आपको याद हो हमने बेनाक स्पेस में डुअल ऑफ डुअल स्पेस की बात करी थी और हमने कहा था कि कोई बेनाक स्पेस रिफ्लेक्सिव होगा अगर वो अपने डबल डुअल के आइसोमॉर्फिक होता है। इफ डबल डुअल इज सेम एज ओरिजिनल बेनाक स्पेस इट इज कॉल्ड रिफ्लेक्सिव स्पेस। करेक्ट है ना? याद है आपको?
Yes, sir.
So अभी हमने यहाँ पर दिखाया कि if H is Hilbert space, H is Hilbert space, H is similar to H dash, okay, and H dash is also a Hilbert space. Now take H dash. H dash is Hilbert space, therefore its dual is Hilbert space, and using this thing, what you get, this is same as H dash, and H dash is same as H. So H double dash is same as H. Okay. So please write a complete proof of this. Complete proof. Okay. So from here, what we are getting that every Hilbert space is reflexive. So this gives that every Hilbert space is reflexive. Okay, then I have something more to say, but we have only 3 minutes left. Let me give you a definition, and then I will stop. So let me give you a definition, and then we will stop. Okay. So आपको ये ऊपर समझ में आया ना? When I said every Hilbert space is reflexive, so what are the things that I use? आपको वो चीजें समझ में आई? हमने क्या देखा? हमने कहा H एक हिल्बर्ट स्पेस है. जब भी हिल्बर्ट स्पेस होगा वो अपने ड्यूअल के वो सेल्फ ड्यूअल होगा. So H dash and H both are isometrically isomorphic. So now you take H dash. H dash is itself a Hilbert space. So it is isometrically isomorphic to its dual. Its dual means double dual of H. So double dual of H, double dual of Hilbert space is same as the original Hilbert space, which gives this result that every Hilbert space is reflexive. Okay. So at the end, I'm leaving you with a definition. What is the definition? Say we have two vector spaces. Okay. Over K, where K is either R or C. Then we define a map. H from X cross Y to K, such that it is linear in first coordinate. So this is the definition for linearity in first coordinate. Okay, and it is conjugate linear in second coordinate or anti-linear in second coordinate. So this is Hx alpha y alpha bar x. Okay. Okay. So this is linear in first coordinate. So here linear, and here this is conjugate linear. H is called skew-linear. It is called skew-linear functional. Okay. So if K is R, then you know alpha bar is same as alpha. So this will be alpha hxy, means it is linear in second coordinate as well. If K is R, then H is linear in second coordinate as well. So in this case, we call H is bilinear. Okay, I will stop here. We will see a Riesz representation theorem for skew-linear functional in next class. Okay, then any question, comment, suggestion, anything? Hello? Hello? बताइए कुछ कमेंट हो, क्वेश्चन हो? अगर नहीं है तो फिर हम लोग कल मंडे को मिलेंगे.
ओके सर.
सिलेबस
ओके देन बाय. हाँ, सिलेबस क्या बोल रहे? कोई कुछ बोला सिलेबस? खुशबू आपने कुछ बोला क्या?
हाँ सर, यूनिट टेस्ट के लिए सिलेबस बता दीजिए सर.
यूनिट टेस्ट के लिए सिलेबस, यूनिट टेस्ट कब होना है आपका? मई में ना? मई फर्स्ट वीक में. तो हम एक काम करते हैं कि आज तक का सिलेबस, आज जितना हो गया, ठीक है?
आज तक का बहुत ज्यादा हो जाएगा सर.
अरे फाइनल में तो आना ही है.
हाँ सर, लेकिन हाँ सर, आना तो है.
पढ़ना आपने है ही उसको, तो अभी पढ़ लीजिए.
पैसा कम कर दीजिए.
थोड़ा कम कर दीजिए.
चलिए ठीक है, इसके बारे में नेक्स्ट क्लास में बताता हूँ आपको. ठीक है
सर.
तो सेकंड या थर्ड वो करेंगे, सेकंड और थर्ड दोनों. ठीक है, ऐसा कर सकते हैं. सेकंड यूनिट, थर्ड यूनिट नेक्स्ट क्लास में बोलता हूँ आपको. ठीक है. और कुछ डाउट आपको?
क्वेश्चन अभी कर रहे हैं तो कुछ आ रहे हैं तो हम आपसे पूछेंगे सर.
हाँ ठीक है. और आप लोगों ने फिर से वो डिस्कस करना छोड़ दिया ग्रुप में. आपने कुछ समय डिस्कस करा था, फिर छोड़ दिया. अभी मैं आपको एक असाइनमेंट दूंगा फिर से, क्योंकि बहुत टाइम हो गया आप लोगों को असाइनमेंट दिए हुए. ठीक है, एक नहीं 2 असाइनमेंट दूंगा एक साथ, तो आप लोग वहां से क्वेश्चन करिए थोड़ा. ओके देन बाय.